This is my coursework for the computer graphics module. I'm going to start off by executing the code and pointing out when the 4 criteria have been met. I'm then going to explain my implementation, specifically going into detail on the criteria. I'll run my code now. For environment mapping, I've implemented a skybox using a cube map, as can be seen by the starry sky behind my scene. The lighting uses the Blinn-Phong model, as well as a dim ambient lighting. The stage shows this best, showing the diffuse and specular lighting of the spotlights, as well as the ambient lighting between them. All of the objects in the scene are mapped with textures. The best example of this is the wall at the back, which as you can see has a different image in each panel. For animated objects, if I press S, the animation will play. As you can see, the dancers rotate and the audience jump up and down. And if I press F, it will stop. To show the implementation of the environment mapping, specifically the skybox, I'll start off in the skybox model class. It takes a length, width and height as input, which are used to define the vertices in code, unlike the other objects which are defined by .obj files. Each vertex contains 3 values, being x, y and z coordinates, hence why the vertex count is the length of this tuple divided by 3. After converting the tuple to a NumPy array, the vertex array object and the vertex buffer object are generated. The VAO is bound, effectively just saying we want to use it, and the VBO is populated with the array of vertices and bound to the VAO. Finally, an attribute is added to the VAO which specifies how to use the data contained in each vertex. Moving on to the skybox material, this takes a file path to a folder which contains the skybox textures and can apply them to the cube map. First, a texture is generated and bound, once again specifying that we want to use it. Next, the parameters are set, specifying how to apply the texture. After this, the images are each loaded from their file path, and their dimensions are stored and they're converted to a string before being added to the previously generated texture as a cube map texture. So there. The use function, it just applies the texture to the currently active object, and that's used in the graphics handler class. Just moving on to the skybox class, it's quite simple. It just contains the mesh and the texture, just to keep them in one place it can be easily accessed. So moving on to the skybox shader, the vertex shader uses only the projection and view matrices, since it has no need for the model matrix. It sets the position, and it passes the texture coordinates to the fragment shader, which just sets the color of each fragment to its corresponding texture coordinate. So in the graphics handler class, we'll focus on what's relevant to the skybox for now. Skybox shader is created using the create shader function, which is down here, and that just compiles the 2 components and then compiles them into a usable shader. Just close that. So after that, skybox class is initialized with a new skybox and a new skybox model and a new texture, which are both the projection matrix is stored in a uniform location, so it can be accessed by the shader, as well as a uniform location for accessing the texture in the fragment shader. Next, inside the render function, which is called every frame, the view transform is initialized with the current camera position and loaded into the view matrix uniform location for the skybox, and its location is set to the camera position. While the camera is actually fixed in place, if it were to move, the skybox would move with it. The texture is applied to the mesh, and the skybox's VAO is bound and drawn, bringing it into the final scene. To show the lighting's implementation, we'll start with the light class. It takes 6 parameters: the position, the point at, which is the coordinates for the spotlight to point at, the cutoff, which is the angle that represents where to cut off the intense light in the middle of the spotlight, the outer cutoff, which is the angle that represents where to stop fading the light out, the color, which is the color of the light, and the strength, which is the strength of the light source. The point at parameter is turned into a vector between its position and that point, and the cutoff and outer cutoff is set as a cosine of the angle to save computation inside the shader. We'll just quickly have a look at the mesh class, just to briefly cover the vertex normals, which the OBJ files which we load contain this information, which is stored as an attribute for each vertex right here. I'll close that. So to go to the vertex shader, the vertex takes the model, view and projection matrices along with the vertex position to set the position. The fragment position, texture coordinate and normal are all passed into the fragment shader. The structure is defined to contain all the data about each light, the same as what the light class contains. This allows the light instances to be passed into a uniform location as a list, and the shader can access the stored information, and that's here. The temp is a vector representing the color of the fragment. It's set to 0 and has 0.2 times the color of the texture coordinate added to it, which is the color of the fragment with only the dim ambient light applied. Next, calculate point light is called on each light in the scene. This takes a light fragment position and a fragment normal as parameters and calculates how the fragment is lit by the light. The base color of the fragment based on the texture is stored. Then, the vector from the fragment to the light is calculated, the distance of this vector is also stored, and then the vector is normalized. The vector from the fragment to the camera is also calculated and normalized. Finally, the vector halfway between the previous 2 vectors is then calculated and normalized. The theta is calculated using the dot product of the fragment to the light vector and the negative distance, which is used to determine if the fragment is inside the spotlight or not. The epsilon is the cosine difference between the inner and outer cutoffs, which is used to calculate the intensity of the light of the fragment, which is then calculated by clamping the theta minus the outer cutoff divided by the epsilon between 0 and 1. This allows for a smooth fade around the edge of the spotlight, so it isn't just an exact circle of light. If the fragment is inside the spotlight, the diffuse and specular lighting is calculated and added to the output of the function. The diffuse lighting is calculated by multiplying the colour of the light by the strength of the light and multiplying that by the dot product of the fragment normal and the fragment to light vector if it's greater than 0, dividing that by the distance squared so it's less intense the further it is from the light, then multiplying it by the texture's colour and the intensity. Then the specular lighting is calculated and added. This is the same calculation, except it isn't multiplied by the texture's colour, and the dot product is instead between the fragment normal and the half vector we previously stored. The result is returned and added to the colour in the main function, which after doing this for every light, sets the final colour along with an alpha channel of 1 so it's opaque. We'll just quickly have a look at scene. The stage lights are initialised by hand. This is because I wanted them in the correct positions exactly, but the lights on the back wall are initialised in code as they need to be evenly spaced, which is that for loop. In the graphics handler, the uniform location of the lights is initialised for all 63 in the scene. In the render function, each light's information is stored in this uniform location to update any changes that may have occurred. This allows the shader to access them and finishes the lighting aspect of the code. For texture mapping, I'll start in the material class. It takes a file path as input and can apply it to the currently active model. It's very similar to the Skybox material class, however it only loads one image. Instead of setting it as a cube map image, it sets it as a 2D texture. I'll go to the mesh class. The .obj files loaded in the mesh class contain texture coordinates, which specify where on the texture each vertex is. This allows the texture to be correctly mapped on the model. This is S and T just here. In the load mesh function, which is here, this data is read and added to each face of the triangle fan generated in the make corner function. So that's this VT here, and this VT just here. The object class is used to contain it alongside a mesh and information about transformations to apply to the object. In the scene class, each object is initialized and added to the objects list. This is also where the textures are initialized. In the render function, the textures are applied to each object in the scene. This is done very similarly to the Skybox, just down here. So the texture use function is called, and the VAO is bound and it's drawn. And that concludes the texture mapping section of the code. For the animation, we'll start in the scene class. The audience and dancers are both generated in code and added to their own lists. This is so that they can be animated separately and the other objects can remain motionless. The animate audience boolean is initialized as false so the animation doesn't start until the S key is pressed. For the audience, the default height of each is recorded and added to a list, along with an integer that represents the direction of travel, +1 being up and -1 being down, and a float representing the base travel speed. In randomized audience, the height of each is slightly randomized to give the impression that they're jumping at different times, and the speed is randomized based on the base speed so they jump at different speeds. The update function rotates the dancers each frame by 90 degrees multiplied by the rate, and the audience is animated to jump up and down by each of their speeds multiplied by the rate in the direction specified. The render function creates a model transformation matrix for each object based on their stored transformations. This allows for the previously calculated movements to be represented in the image each frame. This is also updated in the uniform location so that the lighting is recalculated for their new position. The app class handles the main loop of the program, from which the S and F keys that control the animation are handled. The scene update function is called and the render function is called. To give a quick overview of the code, it starts here where all it does is initialize this app class, which initializes the graphics handler, clock, which is used for the frames, and the scene, which I've been through already. And then it runs the main loop, and in the main loop, when running is true, which means it's still going, it will do this loop, which will check for the events in the pg.event.get, so in pygame events. If it's quit, it will stop running, and then call the destroy function, on which by calling these it will call it on everything. And then it checks for the keys that have been pressed, and then it calls update, calls render, calls tick. In the graphics handler, when it's initialized, it initializes pygame and it initializes OpenGL. It creates both of the shaders and it initializes them both and sets all the uniform locations. And the render function, it renders the skybox, and then it renders the scene by enumerating through all the lights and enumerating through all the objects, applying these transformations, drawing the textures and drawing the triangle fans. And then this will just put that onto the screen. The final class to go through is the camera, which contains all the information about the camera, like its position, the feature, and the phi, the last two of which is the 3D coordinates for where it's looking. This update vectors is here, and this just calculates the forwards vector, the global up, the right, and the up vectors for the camera, which are used in the view matrix.